Right. So I'm indeed immensely grateful to organizers for organizing it, because it's tough to organize a meeting of this size and of this breadth, and it's indeed, it seems like it's a unifying subject. So it brings people from really different lines of thought, and for a long time I belonged to the line of thought just presented in the previous slide, but I'm drifting more and more towards the integrable end of the thing. And thanks a lot for inviting me as well. Right. So this work and this line of thought wouldn't be possible without help and guidance from Marvin Girardot, who passed away 2 years ago. He was truly a mentor and a friend and a collaborator. And from him, we should start counting the time for the exactly solvable, integrable many-body systems. So integrable systems that exist, of course, since Bethe, who solved the Heisenberg magnet, but many-body, the many-particle systems really start from Marvin's paper of 1960. And so the question I'm trying to pose is the following thing. I mean, we know quite a lot by now about integrability. I mean, can we use it finally to serve humanity? And so can we in particular, so any integral of motion, in involution with Hamiltonian or not, it constrains the phase space. So every integral of motion reduces the size of the available phase space by 1. And we know what happens when maximal superintegrability happens, like in the Coulomb atom, where the number of the integrals of motion is just 1 less the dimensionality of the phase space. So the whole evolution is squeezed to a single line, and we get closed trajectories in hydrogen atom. And so can we squeeze the evolution in such a way that we start from an entirely uninteresting state and drive the evolution towards an entangled state? And in particular, I'm interested in beam splitting of heavy objects without actually beam splitting them. So I like to do interferometry with heavy objects without worrying about how to actually beam split quantum mechanically heavy object to 1/2 transmission, 1/2 reflection. So the context behind all of this work is the interferometry with solitons that started from Randy Hewlett, and then sort of is an experiment in Nick Robbins' group in Australia, Coherent in Great Britain, Thomas Bourdelle in the Institut d'Optique. And at first, it would seem that interferometry with interacting gases is a very bad idea, because if you have a non-interacting gas, you split 49%, 51% left and right arm of the interferometer. Well, your fringe visibility will change a little bit, but no drama will happen. If the gas is strongly interacting, then you will have a phase, the difference again, chemical potentials in left and right arms, and you will have an accumulated phase difference. And it seems, and there was a line of works in fact computing precisely this effect, and the gain seems to be very superficial, even though there was some gain seen in Nick Robbins' experiment, probably because you can keep the signal high, and so you can keep the density high. So as usual, the truth is in between the lines, and the thing that nobody tells you about is that all this is just a preparatory work for interferometry with the center of mass of the solitons, as opposed to interferometry with the condensate wave function. So now we're really after the quantum coherent states of macroscopic objects, and there are different points of view on the feasibility of the whole thing. So there's a pessimistic point of view, basically led by Ivan Kostan, that you have to really go to very low kinetic energies. So total kinetic energy of a soliton must be much less than its chemical potential in order to beam split on a beam split of 1/2 without without shedding any atoms, without getting any intermediate values of the transmission, that would work as a reservoir to dump the coherence. And in fact, so you just lose coherence in such a way. And there are two orbital calculations by Zederbaum that are much more optimistic. They basically say that whenever you can allow yourself to lose 1, 2, 3, 4, 5 atoms on transmission, it's not a big deal, because nature would favor the cat states. Would favor a state where the soliton are either fully transmitted or fully reflected. And in any case, experimentally, the closest is the group of Thomas-Bourdelle. So they're already seeing nonlinear effects in transmission, and they're pretty close, not to cats yet, but to fragmented condensates, to superpositions of states with different values of the transmission coefficient, and the cats are coming next. And so, just an advertisement. So if you compare interferometry with large molecules with interferometry with solitons, there are advantages. In particular, when you grow the size of a molecule, the density of internal states increases, and thus it makes it harder and harder to prevent the system from the decoherence. However, in solitons, the gap between the soliton, between the ground state and the first excitation, grows with the numbers of particles. And the reason is that the soliton is an elastic thing. When you grow a soliton, it shrinks. It shrinks because of the self-interaction. And since it shrinks, the uncertainty in kinetic energy, heightened uncertainty in kinetic energy increases, and the gap grows. Of course, I mean, there is an upper bound on how we can grow it, and the upper bound is the transverse vibrational quantum, as we saw in the previous talk. But up to all the way up to there, so if you can really increase the power of your laser to make the transverse confinement stronger and stronger. So this is the limit, but all the way to there, the robustness of a soliton as a robustness of the center of mass of a soliton as a macroscopic object increases with its size, but not decreases as with molecules. And so your transverse confinement would set an upper bound. But there is one problem. And the problem is that the massive soliton becomes harder and harder to split. So the widths in the incident velocities inside such that the given barrier would split the center of mass of soliton by half and half decreases with its mass, and it becomes highly desirable to, in fact, to try to split a lighter object and then entangle it with the center of mass of a soliton. And so, and in such a way, you would bypass this limit. And so the one way, so the way we're suggesting to do it is to use unusual symmetries. And so the unusual symmetry I'm going to present, and already gave a glimpse of this device in one of the talks I gave at another meeting right here about
Galilean cannon means a cannon made in Galilee?
No, it's a cannon invented by Galilei. Right, and so if you're interested, well, we could immediately, I mean, with all these devices, you can go to YouTube and Google Brian Greene, Stephen Colbert, and yes, and then and Brian Greene indeed plays with the Galilean cannon and establishes the highest, establishes the world Guinness record of the highest Galilean cannon in the world. As 5 years ago or so, I brought one with me. It may not work. So let me just show. Yeah. So first. So
shall we take cover?
Actually, it comes with goggles. So right, and the statement is that so if you tune if there is a system of balls falling on a flat surface and reflecting, so if you properly tune the masses of the balls, there will be a situation where the the energy of the whole system will go to the small ball. But for that, in fact, some relationships between the masses must be fulfilled. And if the system is generic, and so in the first make it generic, so I'll just change the order of the balls in the chain. So if the system is generic, then on average, so with the proper average over the mass distributions, the outgoing state is going to be just thermal, and we will see plots for that. So this is a generic. With generic, nothing should happen, and nothing happens. It just decomposes. And now, so I make a mass ratio being equal to 1 to 1/3, 1/6, 1/10, and then you can continue the sequence. It's 2 over n plus 1. And what we're going to see is indeed, first I have to find the whole. So what we're going to see is that indeed, so upon collision, the whole energy will be transferred to the lighter one. And let's see what happens. Hold on. Yes, I have 3 more. Thank you.
Wow. Now you need to repeat it 100 times.
Oh, right. I will have a graph. I'll have a plot with this.
How did Galileo come up with this idea? You know?
This is a good question. It is attributed to Galileo, and I'm not sure how historic.
Mass ratio. I mean,
how this. You can get these mass ratios. You can assign it in the classical mechanics class. I mean, you don't really need.
But there was no classical mechanics.
Good question. So it is a historical name. So
but it's only momentum conservation. If you write energy momentum conservation, you will have this result mass ratio. I did it in my class.
With 2 bosons,
mechanics.
No, but the heavy ball must entirely stop. It just stops.
I believe it's in class.
Yeah. No. You need to have you need to have a well-defined mass ratio. And so why does it work? So there is the explanation for that is that there is a nice map between particle systems and kaleidoscopes or billiards. So you have the d particles on a line or on a half line. So at first you would say, well, mapping particles to mirrors, mapping particles to cavities is easy. Just replace the coordinate of each of the particles by, so let's say the coordinate of this particle I will call x, the coordinate of this particle will call y. I'll get a 2-dimensional system, and this is my cavity, and then there is a hard wall would represent a cavity like that at 90 degrees, and then at 45 degrees there will be a line of interactions between particle 1 and particle 2. The problem is that such a 2-dimensional thing would be highly counterintuitive because it won't have a scalar mass. So its mass will be still that, a mass tensor will be still diagonal, but it will have different entries on the diagonal. And in particular, specular reflection wouldn't work in that case. So there is a nice mass transformation, nice coordinate transformation. Basically multiply each of the coordinates by the square root of the mass. You restore the scalar nature of the mass of this effective 2-dimensional particle. Again, horizontal coordinate is x1, vertical coordinate is x2. The price to pay, depending on how you look at it, is now this second wall is not at 45 degrees, but it is at some angle controlled by the mass ratio. Likewise, for a particle wall contact, you will have a vertical wall. For a particle contact, so we get the line at some angle. So we have 3 particles colliding. There will be 2 hyperplanes of contact, and the angle between them is controlled by the masses. And quite expectedly, so we have 2 pairs of particles that never seen each other. So the angle between the mirror that corresponds to this contact and the angle between the mirrors that correspond to that contact is 90 degrees. So it's like two independent pairs, and so that's all about the map. And before looking at the particle systems, we have to look at the behavior of rays in kaleidoscopes. So imagine that you found the system of 3 mirrors on the street. So with some random angles between the mirrors. If you shine a ray of light through a junction between all mirrors but one, generally speaking, nothing interesting will happen. So we get a ray that flies in some unexpected direction, and with a proper averaging on the mirror configurations, the distribution of these orientations will be just uniform distribution around 4 pi for an ensemble of mirror systems. However, if these three mirrors form, or n mirrors, if these mirrors form generating mirrors of a closed known reflection group, or otherwise known as a kaleidoscope, so the game will change. So when I give this talk, or version of this talk for second graders in the Discovery Museums in Acton, so this is the explanation of what kaleidoscope is I'm giving. So kaleidoscope is a system of mirrors such that you don't know where one mirror ends and another mirror begins. So in particular, in here, if this junction was tighter, you would know where this beam, whether this is an original beam or it's a reflection. This is another reflection, but that's a continuation of the same beam. So the same with the shoulder and the rest of the details. And kaleidoscopes are associated with symmetries of Platonic solids. So we all know about three-dimensional Platonic solids. So Greeks and Pythagoras, they thought they're associated with elements and so forth. So in 2D, the analog are regular polygons. There are high-dimensional analogs. So in 4D, there are 6 of them. And in DD, geometry stabilizes, and there's only 3. So there are only analogs of these 3. And so it becomes completely blurry. And so, if these 3 mirrors are generating mirrors of a symmetry of a Platonic solid, then when you enter through the junction of one pair of the mirrors, you exit through the junction of another pair, or probably the same pair, depending on the polygon. So you will enter through an interesting point, and you will exit through an interesting point. And now you should admit that when 4 balls come together, touching each other, and hit the wall, hit the floor. This is one interesting. This is in fact a junction of 1, 2, 3 of 3 mirrors but one. And then when we exit, when all balls but one are glued to the floor, this is also a junction of 4 mirrors but one, but a different one. And thus the one will start to suspect a connection. And indeed, what happens for this mass ratio 1, 1, 3, 1, 6, 1, 10, and so on and so forth, is that we realize this is one of the realizations of the symmetry group of of a symmetry group of a 4-dimensional tetrahedron. I said one of them because the most well-known you saw in the previous talk. So the most well-known realization of the symmetry of the tetrahedra is atoms of the same mass. So, but there is a family. There is one parametric family of the mass spectra, and so this group lies on another on the other end of this spectrum. And so, in short, so if you just have a found on the street mass spectrum, even if you enter in an unusual state, you'll exit in, and I'll show a plot next, you'll exit in on average in a thermal state. But if it's a kaleidoscopic system of mirrors, then you enter in an interesting state and you exit in another interesting state, or probably you repeat the same state. So to quantify that, this is the classical simulation, and this other plot I'm showing just to show that since it's an integrable system, I can do a four-body quantum dynamics on my laptop. And so what I'm looking at is I'm spoiling integrability, so I'm introducing a noise in the mass distribution. and I'm looking at the transition between the energy equipartition that will happen for a generic set of masses, and of course it's not even a closed system, so it's just a single collision, but they have so many particles and they collide so many times that on the exit they're already on average thermalized. And the velocity equipartition. So I didn't tell about that. Right. So here I'm running the Galilean cannon in reverse. So I'm putting all my particles but one at rest, and then the light particle hits them, and in the end they all start moving with the same velocity. So instead of energy equipartition on the exit, you get the velocity equipartition, and you see that the integrability window shrinks as I'm increasing the size of the system and increasing the number of bodies. So the allowed noise, the allowed deviation from integrability, it shrinks, and so I would expect that in fact in this particular case, so this is another discussion on the Km threshold. So I'm increasing the size of the system, and it becomes harder and harder to keep it integrable. Right, and so in particular, 3 balls would give you a symmetry of a tetrahedron. 4 balls, it's a 4-dimensional tetrahedron. Let me see how much time I have. So let me just spend 2 minutes on the strategic direction we have. So strategically, we're interested in all manifestations of the coordinate beta ansatz. The integrable kaleidoscopes that were classified for us by Donald Coxeter, who in particular invented Coxeter diagrams that classify all integrable billiards, not the particle systems yet. And so those are Coxeter diagrams. So in short, the way to read them is, so each vertex is a mirror, and the edges or not between them and numbers on the edges that correspond to the angles between the mirrors. And so what was known from the 60s is there are 2 useful kaleidoscopes, A and C. So A corresponds to particles on the same mass on a line. So C corresponds to the particles on the same mass on a half line, and then the closed system. So A and tilde is particles on a delta interacting bosons on a ring, and this is and C corresponds to delta interacting bosons in a box, and actually it's C, not B. I mean, this is a mistake. So it should be over here. And it was all known, and it was my little childhood trauma that I mean, this rich variety of diagrams, and they are unused for humanity, as I said. And so we standing on the shoulders of a giant, and in case I just learned, a week ago I learned from Wikipedia who actually the giant was. The giant was Orion, and so the person who's standing on the shoulders of the giant is his servant, who was telling him the way because Orion was blind. So we standing on the shoulders of the giant, we've actually mapped many more mass spectra onto known integrable systems, and this Galilean cannon thing, I don't think anybody have analyzed it from the point of view of the reflection groups. So it's also an answer. So for each of those we have a 1 parametric family of solving problems. And in particular, so the tour de force was the symmetry of the 6 Platonic solid and in 4 spatial dimensions. So that's how this whole story started. So in short, so the diagrams we can treat are those that correspond to a full, as opposed to subgroup, to full symmetry group of a given Platonic solid in some number of dimensions. In particular, as I said, for balls, they map onto a symmetry of 4-dimensional tetrahedron. So this is, and there's a straightforward mass spectra from known kaleidoscopes. So this is our little image. So now, so what do we do? So first, as I said, what do we do to actually to build an interferometer with it? So first, I invert the sequence. So before we had the sequence, so all particles come with the same velocity, hit the floor, and then the lightest flies away. So I revert the sequence. So my heavy particles they stay at rest, and there's a light particle that approaches from infinity. And so since dynamics is reversible, what they're going to get in the end is not an equipartition of energy, but instead an equipartition of velocity. So all of them, they're going to fly with the same velocity, which is already interesting because it's a huge transfer of energy. So basically, the whole energy of the light particle goes in this process to the heavy component, and there's a strong correlation between them because all of them they start suddenly knowing about the velocity of the light particles. So you can imagine that quantum mechanically they would become correlated. So the next thing I do, I add another mirror, and so I consider the following thing. So instead of, and imagine I want to build an interferometer with this massive thing, and as I said, beam splitting the massive objects is a tough thing. So instead I take a light object, I beam split it. So one part, so right arm hits the wall, comes back, and nothing happens to the heavy component. So in the left arm, so light particle goes to the left, hits the first one, returns to its original point. The next one starts moving, hits the next one, returns to the original point, so on and so forth. And then there will be a moment, if the initial positions are tuned well, then there will be a moment when all pairs of rays they intersect, and they intersect at the same time. So at this point, I detect their positions and shove them on a four-dimensional histogram, and start analyzing them. And what is interesting is that if I plot the distribution of the coding of the first particle, I will see nothing. If I plot the joint distribution of three particles, but not four, I will see nothing. But if I plot the hits, if I plot the four-body density as a function of the position of the center of mass plus a small correction, so what I'll see is fringes. And what's interesting as well is that the distance between the fringes will be as if this heavy particle was beam split. So it's really de Broglie wavelengths of the heavy component moving with this velocity. And so in particular, one may think about building a sensor out of it. So you put a phase object in between the heavy and the wall, and start comparing. So what do you compare with? So assume that instead of doing all this complicated thing, you decompose your particles onto individual atoms and do the usual linear interferometry one atom at a time. Of course, gaining accuracy on the way. So improving the visibility of the slope of the dependence on the phase object. And yet, so with the massive. So with using the massive thing, there is a relative gain in accuracy that scales at the square root of the total numbers of atoms, which is expected. I mean, massive is always good. So this is all published. So one philosophical remark is that this scheme is nothing else but the very paradigmatic Schrödinger cat, because you never shove cats off barriers. So what you split on barriers is alpha particles, and then you entangle alpha particles with cats. And in the original example, probably the coherence will be lost on the way because there is no high conservation laws that preserve the coherence from the alpha particle to the cat. So we suggest, in fact, to keep the coherence from here to there. But apart from that, this is the cap. And of course, well, the question all you have is how to, how feasible is all that is. So one of the ideas of generating the mass spectra is to use solitons with an alternating internal state in such a way that the interaction between the different internal states is repulsive, and the interaction between the like states is attractive. So in that way, so solitons will behave as particles, and if they are closed enough, so you can freeze out all the excitations and in the solitons, and then they will really become massive objects. So right, and so I already said that omega torque forms the universal upper bound for everything, in particular to the accuracy. So the mass spectra, and you would say, so I need what, 1/1/3, 1/1/6, 1/10, and so forth. And how do you make all that? So there's a beautiful paper by Satsuma and Iino from the 70s. Basically, you can generate any integer sequence of masses of the solitons in a sequence of quenches of the coupling constant. And so the simplest Galilean cannon is a mass ratio of 3:1, and this one can be done in a fourfold quench of the coupling constant from a soliton, from the basic soliton, to a superposition of two solitons with the mass ratio of 1 to 3. So this is the easiest of Satsuma-Iino sequences. So, and you can, in fact, you can add any kind of imperfection. This 3:1 is pretty simple, and so it is. So this ratio is controlled by another symmetry, which comes from the inverse scattering. Right, but of course, okay. So one can generate a basic sequence, but for larger, for in fact. So for larger systems, for n bodies, not for lots of distribution would need to be thrown away as garbage. And so any experience with number theory is welcome. So we need better protocols for creating the mass ratios. So then mass imperfection. So again, so what I do here is now assume that there is a Poissonian noise in masses. And in fact, this Poissonian noise it's indeed a Poissonian noise, so the massive particles, the absolute value of noise in mass increases as a square root of their size. And so we're looking at the tolerable value of this, of the mass imperfection as a function of the number of particles. And it looks pretty good, so even for 1,000 particles, we can have a 5% noise in the mass ratio, and still, so the outgoing velocities they will be nearly equal. And so this is another bad way to transition from ergodicity to thermal visibility. So it's the system. The large systems become more and more sensitive to the deviations from integrability. So this is accepted in PRA. So in summary, in an integrable system, non-trivial conservational laws are capable of guiding the system from an unentangled to entangled state. The example is a Galilean cannon. So we can demonstrate a square root of number of atoms gain in sensitivity thanks to the entanglement. So the reflection group story is published in this series of papers. It continues, and there is another series on Gross-Ptoevsky breezers and both quantum and semi-classicals. So many thanks to Marvin, to Felix Werner, TNS, Jean-Sébastien Co, Dominique Schneble, Randy Hewlett, Alain Perrin, Roman BBC, and Discovery Museums. And thank you very much.
Eugene?
So for the special mass ratios, do you also need special momentum to have?
So all particles but one are at rest, so I don't.
So that's the only case. It's
Yeah.
not like I can choose arbitrary initial moment and then I will still have some symmetries.
No, the symmetry will be there. So the special set, it corresponds to a very special orientation of the ray in a kaleidoscope, but the symmetry will go nowhere. I mean, you don't need special momentum. I mean, the symmetry will be preserved. The manifestations of it will be harder to see. That's it.
Okay, for example, like in the usual beta that's which have individual momenta conserved the collision. So here you're saying only a special collection of momenta would be conserved. Otherwise, we will probably still get special trajectory, but it will look very awkward.
No, all of them will be conserved. It's not so the integrals of motion are not that easy. They're different functionals of the individual momenta, but they will be still n integrals of motion. Yeah, there's exactly like in the Lagrange. They will come. They won't be as easy as moments of the momentum distribution, but they will be still linear functionals of the momenta. So you get all the conserved quantities will be there. They're more difficult. I mean, they're related to so-called Chevalier polynomials, but they are as fundamental and as one body as they are for the Lagrange.
Other questions? If not, join me in thanking Maxim.